Okay, our next speaker is George Hathaway. So we'll go ahead and get started here. I know that was an awfully short break, but we're at least keeping the schedule pretty well, so we'll have plenty of time to get to know each other better during dinner. I find that what goes on at lunch and dinner is often just as important as what goes on the floor of the session. That's why we try to keep on schedule so that we have at least those times that we can spend together. George Hathaway is a professional electrical engineer from Toronto, Canada. He's involved in non-conventional energy and propulsion research. He's been doing that since the mid-70s. He assists inventors in testing and commercializing inventions. He also helps investors locate potentially worthwhile inventions for development. He's hosted and organized 2 influential symposia on advanced energy and propulsion technology. He lectures extensively on the topic. He also teaches computer graphics at the college level in Toronto. Let's give a welcome to George Hathaway.
Thank you very much, Bo. Out of the way. And you may remind yourselves of my last year's, or 2 years ago lecture. Does everyone hear me back there? Can you hear me back there as well? Because I tend to move around a lot, arm waves, things like that. So I'll try and stick close to the mic. Let's see whether we can.
We're supposed to clip this one too.
Yeah. Just a second here.
Yeah, the clip's missing.
This is okay.
I'll get this.
Is that better? Oh, is that better? All right. 2 years ago, I was privileged of addressing the Tesla Society, and I gave a rather dull presentation with a few tapes and overheads and things like that. Put a lot of people to sleep. This time, I'm going to really spruce things up with a lot of equations. You now have 30 seconds to leave the room if equations start to give you the creeping heaves. I'll try and minimize their impact, so what I suggest to do is just kind of relax, put your feet up or your head back or whatever, take your shoes off and let all of these things just flow right through you. If you are kind of Zen inclined, it might make a little more sense. So, why don't I get started initially here, because I have a whole lot of stuff to say, and as usual, not much time. Yes, there are only 49 equations, and I think that you should have them all under your belt by the time I'm finished, one way or another. So, to get this off to a reasonable start, I'm going to depart from my usual arm waving, as I suggested I was going to do just a while ago, and actually read from some of this presentation, which you will find published, I hope, in the symposium proceedings for the 1990 symposium.
Okay. There we go.
Is that any? I think that's just about. Okay, that's for tapes. Fine. The paper that I'm giving here attempts to draw together the most practical aspects of work by researchers who have investigated or are currently investigating the use of vacuum fluctuation or zero-point energy for practical applications. I'm going to talk about the work of René Louis Vallée, Harold Puthoff, Fred Alzafon, Alexander Vasilyevich Janetsky, and Maury King, who's here in the audience. And these seem to be at sufficiently advanced stage to allow initial experiments to be designed. Only the essentials of their theories will be presented. You may question that after I'm finished. But chiefly those aspects from which real-world physical apparatus and order of magnitude measurements can be deduced. The work of other researchers, which may have a bearing on the subject, will also be briefly touched on. The task of characterizing this kind of research in engineering terms is very difficult for a number of viewpoints. The primary difficulty lies in the sheer novelty of the suggestion that such energy conversion may be possible at all. As well, the general esoteric nature of the theoretical basis of most of the work related specifically to zero-point energy, namely quantum electrodynamics, has prevented more physicists from such undertakings. The resulting lack of parametric equations, which can be translated into testable hypotheses, invoking actual laboratory apparatus, as opposed to Gedanken experiments, for instance, might indicate that the paper that I'm about to give may be premature. However, I hope that it will demonstrate that the eventual discovery of techniques to extract and convert useful energy from virtual vacuum fluctuations, or zero-point energy, is not an ivory tower pipe dream, but more a matter of nuts and bolts. And I hope it'll serve as a rationale for those engineers and researchers to keep a close watch on vacuum energy physics development. Let's start by characterizing the vacuum itself. Very briefly, there are two terms that are generally used in this context. One is zero-point energy, and that which remains after an enclosure is pumped completely devoid of all matter and thermal radiation. Although this is the lowest energy state of matter, its energy is not precisely zero. Vacuum fluctuations, on the other hand, are those virtual processes going on beyond the range of direct measurement, usually smaller than the Planck length. In general, however, the two terms can be used synonymously. A very brief foray into characterizing the vacuum and vacuum fluctuations. In 1911, Max Planck proposed that a harmonic oscillator in its ground state, or lowest energy state, does not have zero energy, but that of equation 1, which is something you may be able to see up there, E equals h bar omega over 2, where h bar is Planck's constant divided by 2 pi, and omega is the radian frequency of oscillation. Imagine a mass suspended on a spring. That's first picture. We'll be zipping around doing a lot of hand-eye stuff. There on the left, picture number 1, which exhibits damped oscillations. After a sufficiently long time, one would think that classically there would be no energy left in the system. It would die down to zero. But according to Planck, there would always be some small jittery motion, Zitterbewegung motion, caused by localized fluctuations of the neighboring vacuum, analogous to the effects of Brownian motion, as you see those little fluctuations continuing off into infinite time. As h, however, is a very small number, it's approximately 6.6 times 10 to the minus 34th joule seconds, one would think that E in the first equation represents a very small number. However, Nernst in 1916 assigned this value not to the entire energy content, but to each mode of oscillation, i.e. each frequency and direction of the random fluctuations. Imagine an electromagnetic cavity resonator the size of the universe. An effectively infinite number of modes of electromagnetic radiation, therefore, would be supported within its boundaries. This allows, unfortunately, the concept of an infinite zero-point energy density, something which many physicists have concerned themselves with, suggesting more or less arbitrary high-frequency cutoffs and other renormalizing techniques to try and put a limit on the so-called zero-point energy density. Another feature of these quantum fluctuations relates to the Heisenberg uncertainty principle, which says that beyond our limits of measurement, namely dimensions generally smaller than the Planck length, which is 10 to the minus 35th meters, virtual processes can go on which we cannot directly measure, but are nevertheless allowed and governed by physical laws. In particular, matter-antimatter particle pairs, positron-electron, are being spontaneously and continually created and annihilated. This vacuum fluctuation process is too fast and at too small a scale to witness or directly measure. However, theorists such as Alzafan and Vallée, as I will get into momentarily, consider that it's just by such a train of creation, annihilation, and creation that electromagnetic wave propagates, amongst other things. Another important consideration involves the invariant nature of zero-point energy. It can be shown that the density of normal oscillation modes, these directions and frequencies, per increment of frequency, the omega, in a cavity is ding number 2. Equation number 2 there, you see the little circle beside. There we go, thank you. Where C is the velocity of light. Therefore, the zero-point energy density per frequency increment called the spectral energy density is found from equations 1 and 2 as equation 3. And it has a cubic variation with frequency. And to see that, picture number 2 will show diagrammatically how, you want to lift her up a wee bit, the vertical axis is the density of modes per frequency, and the horizontal axis is the frequency, and there are little increments of frequency you have increasing as you go out, and frequency you have increasing number or density of modes of frequencies. This cubic dependence on frequency is very important, and by applying the Lorentz transformation it can be shown that the spectral density is Lorentz invariant. And thus, an observer in a non-accelerated uniform motion somehow magically measuring this spectrum will measure no Doppler-induced frequency shifting to indicate its presence. Hence, even though the zero-point energy may be enormous, it will not be measurable from inertial frames. It may be detectable, however, from accelerated frames. And Sakharov suggested a connection between the zero-point energy spectrum of an accelerated observer and gravity, not as a primary field in itself, but rather an induced effect. Parenthetically, the completely isotropic nature of the vacuum fluctuations suggests the possibility of analyzing its properties perhaps analogously to another mathematically self-similar set of entities, namely fractals. Perhaps there are an infinite degrees of substructure in the vacuum as well. I've never heard of anyone examining the zero-point energy as a kind of a fractal state, but perhaps Maury King or someone be able to delve into that. And if we go ahead and integrate the spectral density function over frequency up to some arbitrary cutoff frequency corresponding approximately to the Planck length, we get equation 4, and that's where Wheeler and a lot of people have quoted his number. The energy density approximately 10 to the 115th, 10 to the 115th joules per meter cubed. This exceptionally high value has been questioned by many people, including Alzafon and Vallée, who take issue with the rather arbitrary choice of cutoff frequency. Recently, Hal Puthoff has shown that the source of the zero-point spectrum is the motion of charged particles throughout the universe, which are themselves undergoing vacuum fluctuation-induced motions in a kind of self-generating grand ground state of the universe, unquote. But is it possible to extract some useful, manageable quantities of energy from this huge random fluctuation reservoir and perhaps alter the local gravitational field at the same time? We shall now examine theoretical and practical attempts to do so. First, starting off with the Casimir effect. In 1948, that is, Casimir calculated the inward force on two uncharged parallel conducting plates. Figure 3, please. Over there, two plates, two conducting charged plates separated by distance s, Fc being the Casimir force inward. When two conducting plates are separated by distance s, they act somewhat like a cavity in which only certain electromagnetic modes are sustainable. Whereas outside the plates, an essentially infinite number of zero-point modes exist, each with its own energy. Between the plates, only those modes where s equals an integer number of half-wavelengths are sustainable. Hence, the energy density is less between the plates, and they're pushed together. At least that's the generalist approach to that activity. Using the high-frequency cutoff considerations related to plate thickness, one can calculate the energy of the plate system as equation 5, and where A is the plate area, you can see it's inversely proportional to the separation. And this leads to a force per unit area in equation 6, which goes up as the inverse separation distance to the fourth power. And to give you some idea of what this means, which is what I'm trying to do for engineers in the audience and others, a force of 0.013 dynes, or about 3 times 10 to the minus 8th pound force, results from a separation of 1 micron. So if you can get things 1 micron separated apart, you'll get a force of about 0.013 dynes. This pressure was actually measured between two mica cylinders, and they were put orthogonally and measured. And it was approximately 1.5 psi, to give you some other kinds of measurements, to give you an idea, or 10 kilonewtons per meter squared, at a separation of about 1.4 nanometers, that's 10 to the minus 9th meters, by Israel Akvi and Tabor in 1972. And that is a very good lesson in that paper of experimental preparation and of witnessing an effect that's very difficult to achieve. It's also important to note, for those who think that this is also much arm-waving, that the Casimir force is evident in certain high-precision EDM and micro-milling machining in industry, where you have the contact forces between the tool and the workpiece have to be constantly repositioned to take into account the Casimir force. So they're actually, people are having to take this thing into consideration. I would like to find out what the Casimir calculations were undertaken for the scanning tunneling electron microscope. I don't know whether anybody's taken a look at that microscope that continually readjusts its height above the surface, whether Casimir is acting there too. One of the first engineering ideas, however, to extract useful energy from the vacuum is attributable to Robert Forward. and called by him the vacuum fluctuation battery. You can imagine a very thin, wide metal foil helix, like a slinky, and by charging the helix with electrons, for instance, the Coulomb repulsion between the adjacent plates could be adjusted until it's just slightly less than the Casimir force, and the whole assembly then would collapse like an accordion, and you could get energy from that. However, you'd have at least the same amount of energy required to expand the plates again, so I don't think there'd be any net excess energy resulting from such a battery. However, Puthoff has recently suggested that if we could produce an inexhaustible supply of such devices, and it took less energy to make each one than was released through the Casimir collapse, and each device was discarded after use, then there may be a net positive yield from the zero-point Casimir pinch. Such a device might be a cold, dense, charged plasma, in which charge condensation takes place by radial Casimir forces, figure 4, perhaps similar to the ball lightning witnessed in photographs of Tesla's apparatus, and perhaps, a big perhaps, in photographs of Coulom's research. It may be that Chernetsky in Russia as well, who's experimenting with these similar processes, has observed this kind of thing. Figure 4, representation of a radial pinching by Casimir collapse. One might also speculate on the possibility of producing a vacuum fluctuation laser. As demonstrated above, just such a cavity below cutoff, as a cavity below cutoff suppresses vacuum fluctuations, a resonant cavity could enhance them. Perhaps by enclosing a main resonant cavity within one or more leaky cavities, only certain modes stimulated within them would be allowed into the main cavity, where amplification may ensue. The leaky cavities might act as mode separators or discriminators, or even mode downshifters if suitable geometry is chosen. Thus a sort of vacuum fluctuation amplification by stimulated energy resonance, or V-phasor, might be proposed. Speaking of Puthoff, why don't we discuss, I'm sure you're interested, the source of gravitational interactions, which is a paper that he has recently come out with in Physical Review. And he expands on the Sakharov idea regarding gravity, already mentioned above, and combines the effects related to the Casimir force to show that gravity can be considered equivalent to long-range van der Waals forces. These are the forces involved in chemical bonding between molecules and have been studied in this regard as well by Leon Dragoni. And I'd like to mention here briefly an unfortunate passing of Leon Dragoni. Several months ago, he died, I guess at I would say the peak of his analytical powers, and it's most unfortunate that he has passed on. The gravitational force is then seen to be due to the radiation fields rather than the induction fields, as pointed out by Vallée as well, as we'll discuss. Puthoff starts, and I'll zip through this fairly quickly, just give you a flavor of it, by considering particle field interactions, first thing. So a particle and a field, described by the summation of forces equation, a fairly standard approach for a harmonic oscillator of mass m. Are we at 7? Here we are, equation 7, the top left. Mass m and charge q oscillating in the x direction with an accompanying electric field E. That my curly E, EZP, or ZP as I should say down here, is the electric field due to the zero-point energy, where the electric field is the sum over plane waves of random phases. Here the first term, the m r dot, represents the particle inertia, standard kind of thing. The second is the restoring or spring force, which is proportional to the square of the oscillation frequency omega. And the third term accounts for the radiation damping, the first term on the right-hand side of the equation, the q squared term. That's radiation damping or radiation reaction, and the last term is the electric field force, F equals QE. This equation can be rewritten in terms of the effective dipole moment instead of M and R, and we see equation 8 as the result of that, where gamma is the radiation damping constant, and the second and third parts of the terms of that equation are negligible compared to the first and last, and then Puthoff does some fancy mathematics to average and integrate over phases and assumes a cutoff frequency, omega c, which finally ends up with the internal fluctuational energy of the particle as equation 9, average energy, which is proportional to this cutoff frequency squared. Then from that he generates the particle effective rest mass, which is also equivalent or proportional to the omega C squared equation. Pardon me, keep going down. I don't have that on there. And it generates the mass involved in a gravitational interaction. His next step, put-off, that is, calculating the average force between particles. The first one was particle field, and now it's particle-particle. And he generates a potential using analysis of van der Waals forces due to Boyer, giving him equation 11, where S is the interparticle separation distance again. This U, or potential figure. And it goes on, and I'm going to try and cut through a lot of this stuff. And he finally estimates a cutoff frequency, which is very important, omega c, using the equivalence principle and spectral ZPE distribution in accelerated frame, again due to Boyer, and results in equation 14, which is I'm going to try and zip to, where omega c, the cutoff frequency for the high frequency jittering motion that is inherent in the 0-point energy, that's what we're talking about, the high frequency limit of that, is given by that equation, where K in the denominator is the gravitational constant, 6.7 times 10 to the minus 11 meters cubed per kilogram second squared. Substituting that, finally, into equation 13, about 14 into 13, results in Newton, kmm over r, or s squared. Km squared over s squared, the standard Newtonian gravitational attraction. So he's gone full circle from, I shouldn't say full circle, he's gone from a quantum 0-point understanding to a macroscopic Newtonian approach. Equation 14, by the way, results in extremely high cutoff frequency in the order of 10 to the 43rd hertz. I don't have that up there. But this is primarily based, as I say, on the Planck length consideration and more esoteric quantum considerations. As shown a little later in my talk, based on more straightforward assumption involving dimensions on the order of the Compton wavelength, Vallée calculates the cutoff frequency to approximately 10 to the 20th hertz, still very high. By the way, this figure differs from Puthoff's figure by approximately the ratio of the Compton wavelength for electron to the Planck length, just out of interest. In any event, the importance of these limiting factors, primarily the limiting cutoff frequency, and as we'll see, the limiting electric field strength on the energy of the vacuum, plays a crucial role in determining the interactions between vacuum fluctuations, gravity, and matter. More germane to the purpose of this paper, the cutoff energy will tell us whether we can possibly ever hope to achieve any measurable energetic or gravitational interaction using state-of-the-art instrumentation available now or in the near future. I hope to show that we're just about on the edge. I have a section here on a guy named Moray B. King, cohering the 0-point energy, but he's much better at explaining his understandings of quantum vacuum activity than I am. But suffice it to say that in his book, Tapping the 0-point energy, there is an equation that relates, I don't think I have it up there, can you drop it? No, go on to Alpha next. That relates the plasma frequency of resonant modes in a plasma, to the number of charge carriers and the masses of them, whether protons and electrons, etc. And I took that equation and did put some numbers into it, and choosing a suitable carrier density of about 10 to the 18th particles per meter cubed, which is a little higher than some standard plasma kinds of activities. The frequency for protons is approximately 200 megahertz, and that for electrons is approximately 9 gigahertz. It is therefore apparent that these frequencies, common in modern high-frequency and UHF, or ultra-high-frequency plasma work, are well below the frequencies at which interactions with the vacuum may appear, given by these cutoff frequencies. It may be, therefore, that some tiny degree of coherence may be achieved in these kinds of systems, these plasma bucking systems, but unless great care is taken, it will be so swamped by system noise as to be indistinguishable from other contributions. However, it is necessary to continue devising such experiments as Moray and others are doing. And now I'd like to go on to the work of the Russian Alexander Vasilyevich Chernetsky, who some of you have heard about from a press release that was circulated in the so-called underground emanating from a guy named Andrei Samokin. How many of you have actually seen that press release or heard of this guy, Chernetsky? Just out of interest, I'd like to see, well, there's a few people who have. So I'll go through it to describe it a little more briefly, a little more fully, instead of making it brief. Another group of researchers intent on producing useful energy from the vacuum is working with Professor Alexander Chernetsky in the USSR Ecological Union in Moscow. Since the early 1980s, Chernetsky has been working on a phenomenon he discovered in the mid-70s while working with various plasmas and electric arc discharges. In designs used for research and industrial purposes, these are basically two electrode systems enclosed in a container which can contain a gas at various pressures and be subject to an external magnetic field. Just what we'd call an arc discharge. In one configuration, the device is known in the USSR as a plasmatron and produces an extremely hot ionized gas plasma stream for various applications, including surface preparation and metallurgy, deposition in electronics, and general high-temperature research work. In smaller demonstration devices, however, the plasma is a simple electric arc or spark and is maintained at atmospheric pressure in air, similar to the one that Toby showed you on his Tesla coil, and most other people have seen Tesla coils. And we'll have a much more detailed examination of arc discharges in the paper by Professor Pappas, who will be succeeding me in a short while. So I suggest you stick around for that one. While studying these devices, under certain conditions of external magnetic field intensity, configuration and duration, and in certain regimes of current and voltage through the plasma, an unusual energy imbalance was discovered. Over a broad range of frequencies, the energy dissipated in a load connected in series with the arc discharge was at times seen to be greater than that supplied to the circuit from the mains, from the wall circuit, for instance. Energy amplification up to 10 times was claimed from a continuous self-generating discharge, or SGD as it was called. As many measurements have been performed over several years by Chernetsky and others to confirm the observations, but no independent measurements have been made outside the Soviet Union, to my knowledge. It is known that in certain operating regimes, an arc of this type, it can exhibit a negative resistance, a phenomenon used today in certain semiconductor diodes, for instance. It is also known that condensers and inductors in circuit can affect a substantial phase shift between the input voltage and current, which appears to the untrained eye as a change in input power, called reactive power. Chernetsky is firmly convinced, however, that he's not being fooled by any of these well-known effects. In one small demonstration of the effect, 6 clear 220-volt, approximately 60-watt lamps are mounted on a small box, about, I guess, a couple of feet by a foot wide. In addition, there's a power cord to be plugged into the wall and a small spark gap on top of the box. The power cord is plugged into a wall socket of 220 volts, 50 hertz, and the small spark gap is open to the atmosphere and has a knob on one end for adjustment, across which a continuous bluish multi-streamered spark can jump while in operation, only about less than a 1/16 of an inch. Plugging in the power cord and closing the gap results in all the lamps glowing with equal brilliance, namely a dull yellow, as if operating at less than half voltage. However, slowly the gap is opened, and at one critical point when the arc is ignited, which is not hard to achieve or maintain, 2 of the lamps in series with the gap, glow much more brightly than the other 4, which continue to glow at the same intensity. These other 4 are connected to the input, to the mains. The voltage from the mains is constant throughout the duration of the demonstration. The increased energy to light the 2 lamps to great brilliance is claimed by Chernetsky to come from the vacuum energy of space. Now, Chernetsky has a theory, which I will try to summarize, which involves electron flow being pinched. Can I have that? Thank you. This man's way ahead of me. There are 2, there's an anode and cathode, negative and positive. That end view, by the way, is just looking down the plasma tube. There's an anode and cathode, negative and positive. That end view, by the way, is just looking down the plasma tube. There's a plasma that constitutes the arc between the 2 electrodes, and at one point there is a pinch, perhaps a Casimir type pinch. Strong magnetic field is established in the discharge by the current flow, and this in turn causes electrons to try to fall in toward the axis of the discharge, and the resulting electron motion is cycloidal, as I'm trying to messily display there. Czerniewski believes that this electric field is sufficient to radially polarize a tiny portion of the virtual pairs, positron and electron, as they emerge from the virtual state before being annihilated. And this adds to the energy of the circuit. I'll go through this one. The Russian group plans to produce an integrated energy amplifier and traction motor system in collaboration with researchers in other parts of the country. In addition, there are plans to produce a 50 kilowatt amplifier from 10 kilowatts input for direct use in heating and lighting and other applications not needing sinusoidal wave shapes. You can imagine the wave shape from that is not sinusoidal. Direct propulsion from polarization of virtual pairs using the SGD method may also be investigated, as are more prosaic industrial applications of the plasmatron. Now, I would like to proceed to an American who is not well known. His name is Dr. Fred Alzofan, and he had developed in the 1960s a unified gravitational theory, which led him to propose several experimental tests, and that's why I am interested, and most engineers would be interested, is lots of theories, lots of arm waving. Let's get someone to propose a couple of experiments that we can do. Fred Alzofan has done just that. The theory is based on the single main assumption that light signals are noisy. Okay, try and think about that one. And what we measure is only really the RMS value of the electromagnetic signal that has a noise component derived from random virtual vacuum fluctuation processes. According to the theory, the propagation of light takes place by a continual process of virtual particle pair production and annihilation, etc. An altered metric, therefore, of space-time due to these processes results in new field equations of motion and 4 new potentials. Specifically, if we write the usual expression for propagation of plane electromagnetic waves in a vacuum in the x direction, we get equation 17. This is on the left side. And by introducing these additive correction terms to account for the fluctuation processes that make light not a pure, you might say, zero-phase noise sinusoid, these correction terms resulting from random fluctuations, whose RMS value is 0, we produce a new metric, and we get the right-hand side, you might say, of that arrow, equation 19, where we have additional terms, x naught, and for the space term, and the time term is altered by h, which is Planck's constant, over mc squared. Now, the h over mc squared, in effect, represents a phase correction term, during which time the creation and annihilation process occurs, and whose RMS value is 0. We can look at that somewhat diagrammatically in Figure 7, where on the top we have what might be considered a classical idea of a sinusoidal waveform, or a photon blasting through an electromagnetic wave going through space. In the noisy photon, or noisy EM approach, which is Alzofan's, there are creation and annihilation times. And this might be considered a phase noise, and however, over sufficiently long number of cycles, the average phase is 0. The RMS value is 0. So over sufficiently long periods, which can be very short, of course, because the wavelength is so small, one would not see any difference, or one would not detect that a light signal could be noisy. However, this is, as a characterization of random processes, the behavior of this electromagnetic propagation and vacuum fluctuation effects are now described by quadratic expressions and are radically different, therefore, on average, from the effects described by linear equations, even though the mean energy and momentum associated with the fluctuation process is 0. Using these considerations and solving the various propagation equations results in potentials which vary approximately as equation 20, I believe. Are we at Alzofan? Yes. Way over in the corner there, under the word orientation. By the way, if you drop it down, Alzofan talks about gravitational interaction by dynamic nuclear orientation. That's what I'm going to... I forgot to give the full title of this section. Now, notice that in equation 20, this is an equation for how a potential varies with radial distance from it. And notice that there's, in the denominator, an r squared plus a corrective term, h bar over mc all squared cubed. What does this mean, George, you may ask? Well, what it means is shown in Figure 8. and is of importance when one considers the problem that is continually one comes up with when one says, what happens when we have two particles whose separation becomes zero? Does their energy become infinite? Well, classically, yes. But if you take Alciphon's potential, which has that corrective term added to the denominator, instead of having the energy go to infinity, the potential here in this case, going to infinity as r drops to zero, the potential does not go to infinity but goes to some finite value. This allows him to proceed to develop a series of coupled equations which involve a gravitational component. Now, where should I go to? In proceeding by coupling these equations of motion to matter radiation fields and the Bose-Einstein fields and things of that nature, he finally arrives at equation 21, which is the energy associated with particles in a gravitational field. And this equation 21, there, if you can see it at the back, hope you can, is basically of a particle with a magnetic moment epsilon h bar over 2mc, which is this component epsilon h bar over 2mc times a standard magnetic field, or a magnetic field impressed from an external source, interacting with a magnetic moment of q prime h bar over 2mc, which is governing or multiplied by this magnetic field, which is the magnetic field due to the associated with the random zero-point fluctuation processes. In this expression, the large A, by the way, is the vector potential, the P is a momentum, and the sigma is a Hermitian matrix defining particle spin, and the zeta is another spin matrix resulting from the fluctuations. And Q prime is an average charge or effective charge within virtual processes. The H naught field, H sub naught, is a high-frequency vacuum fluctuation magnetic field not directly observable, but whose RMS effects are observable. These are primarily spin, and associated with the gravitational interaction and attraction. By the way, Professor Shinichi Seiki, some of you may know, argues along somewhat similar lines to this. Alciphon asserts, along with Vallée and Puthoff, that the basic feature responsible for the stability of matter is also responsible for gravity. And this is equivalent to saying within the theory that the Compton wavelength remains constant for elementary particles. But as shown above, in a couple over there, the Compton wavelength is a measure of the extent of the cloud of virtual processes around a particle, one might say of the matter radiation field and the mass energy density distribution associated with a particle. If a second particle comes into the vicinity of the first, this density distribution is altered to give us equation 22, which is squeezed in there, where the Compton wavelength is corrected by a factor delta m, which is this additional mass, which is approximately equal to h over mc times 1 minus the delta m over m. That is less than 1. 1 minus something smaller than something bigger is always less than 1. So the Compton wavelength decreases. The overall extent, the overall result of this is that objects tend to attract each other to maintain an energy balance. And this is his very brief explanation for gravitational attraction. Now, how can we use these kinds of concepts, especially this equation, to see whether we can alter the gravitational effect? According to 21, that long equation there, it should be possible to alter the gravitational attraction between two bodies by affecting a change in the energy E. The agents through which this can be done are the magnetic fields H and H naught in 21. And this leads us to consider the effect of altering the spin magnetic resonance of atomic nuclei and what effect this would have on the energy. And it's a process known as dynamic nuclear orientation. I'm not going to go into dynamic nuclear orientation except to show very briefly that when atoms, nucleons have particular spins as indicated by these three nucleons with their arrows, when there's no field, in the presence of a magnetic field, they tend to line up and relax into a cool state, you might say, a lower energy state. And then when that field is taken away, they randomize themselves by thermal processes and virtual processes, and when things are timed right, gravitational energy can be sucked up by this relaxing process, by this thermally relaxing process, and this might allow the production of a reverse gravitational or a reduction in gravitational potential in the nucleons of this material. Time taken for this process is relaxation time must be greater than the thermal collision time, and you have to get everything right. But to give you an example of what this means in terms of measurable quantities, he uses dynamic nuclear orientation, or NMR. It's essentially an enhanced NMR, a nuclear magnetic resonance technique, plus his theory to propose that a specimen of aluminum with iron inclusions pulsed at low gigahertz microwave frequencies in such a configuration will lead to a lessening of the gravitational attraction to the Earth. A fixed magnetic field of a few hundred Gauss and pulse widths of a few microseconds are required. Ideally, the process should take place at liquid helium or liquid nitrogen temperatures. If, to give you an idea of what this means, the iron to aluminum nuclei ratio is approximately 1 to 10, about 1 joule of gravitational energy can be removed from the Earth's 6 times 10 to the 4th, or 60,000 joules per gram of field energy per pulse. Thus, an appreciable part of it would be removed in several seconds. And in fact, if you were pulsing it at 500 hertz, in 2 minutes you would, according to this equation, completely nullify gravitational field on those specimens. It gives you an idea. These are engineering realities. I mean, we can produce 2 microsecond pulses, we can produce low gigahertz frequencies, and we can produce the kinds of fields that are required, and we are hopefully going to see that kind of process one day soon. The last person I want to talk about to you is René Vallée, a French engineer and physicist who wrote his magnum opus in 1970 in Paris, called the gravitational electromagnetic energy, or synergy theory. And in it he postulates the existence of an energized medium, such as the vacuum energy of space or the zero-point energy, and an upper limit to the electric field. He begins by defining inertial vacuum reference frames and all sorts of stuff, which I don't have time to get into. But eventually, he shows that there must be an upper limit to the electric field strength in any place in space. You cannot keep increasing the electric field strength to infinity. What happens is, at a particular cutoff frequency, particle pairs are produced. And he calls this the disruptive limit, where the fabric of space, you might say, is torn apart, if you can imagine that, and particles are produced, positron-electron pairs. These he also calls divergent zones, and they are analogous to the process of cavitation in fluids, where the physical properties of the medium are modified by the passage of an electromagnetic wave. Now, we can model those kinds of activities as waveguide cavities, these little divergent zones in which particle pairs are produced when the electric field strength reaches a critical value. You can model those as waveguides with perfectly reflecting walls, and he's done so because he's an electrical engineer. He likes to do such things. I like to too, because I can understand them. And he uses a standard average inductance and capacitance and characteristic impedance and resonant frequency. And finally comes up with, where do we have an equation set here? I don't want to, is that one of my, no, I'm beyond that. How we go to 26? There, for instance, to pay, equation 27, by decomposing first of all, by setting the maximum energy, transmitted per period as Emax as a standard equation relating to the charge and the capacitance and the inductance and the current. When the limiting value of the field is reached, when the limiting value of the electric field is reached, the electric and magnetic components are equal, and thus E equals simply Q squared over C naught, not a half. And the average value is 2Q squared over Cm. But we can decompose 1 over Cm according to equation 27, and the result is that equation 28, I guess beside equation 27, E equals 4q squared Z naught, which is characteristic impedance pi f, where f is the frequency, gives the energy as a function of frequency. You might start to make a connection here shortly, where Z naught is the characteristic impedance of the medium in this divergent zone and is equal to just a little over 1,000 ohms. By the way, K naught in that Z equals, equals just a little over 1,000 ohms. Equation 28 expresses quantification of Q, quantification by Q of energy of the vacuum medium as a function of frequency at the level of these divergent zones where these particles are produced when the electric field strength reaches its critical value and is therefore a model of a photon. At other places where the electric field strength is less than this disruptive high cutoff, no photon exists and an energy continuum exists governed by Maxwell's equations. Vallée makes the obvious correspondence between 4q squared Z naught pi and Planck's constant, h, but notes that when the energy is stretched over a wavelength, there are two maxima per cycle which must exist opposing the fields, resulting in h, in equation 30, please drop her one down, Blair, thanks. Equation 30 on the left-hand side, h now is not a universal constant according to Vallée, but is equal to 8 pi q squared k naught times the square root of mu naught over epsilon. And that is no longer a universal constant. It is a derivable constant and alterable. It appears that, to a good approximation, the permeability, however, mu naught, is invariant. This suggests that the frequency associated with quantum vacuum-determined phenomena is independent of energy density, and that the stability of the elementary particles could correspond to resonant frequencies on a distribution curve of vacuum energy. But that can be derived from this examination of derivation of Planck's constant. Note as well that fine structure constant alpha naught also falls out of that, as just beside equation 30. Now, getting back to this waveguide model of propagation, and assuming a dipole, a continuum of dipoles, it is not unreasonable to suggest a certain cylindrical model which would allow us to calculate this, what this upper limit of the electric field strength is before particle pairs are produced. And let me see what I've got here. No, I think we're back on equation 31. Pardon me, 32. And Vallée takes a cylindrical model and an integral number of wavelengths around this cylinder for a photon and calculates the disruptive limit of the electric field on the surface of that cylinder as 38 times 10 to the 15th volts per meter, and a corresponding frequency of about 10 to the 20th hertz. These considerations, by the way, also allow him to derive the Bohr magneton. As I'm sure some of you have studied miscellaneous unified field theories, everyone who has one can derive everything from them. Vallée is no exception. He likes to be able to derive everything from these kinds of things. Okay, I'm going to zip on and give you, wrap this up by showing some actual measurable parameters which are associated with some of these equations. And one other equation of great importance is equation 38. Here we are. The energy associated with a gravitational, the energy per volume associated with a gravitational field is rho naught, which is the density of energy in the zero-point field, you might say, or vacuum field, minus the gravitational potential gamma squared over 8 pi k, where k is the gravitational constant. Using this relationship, by the way, Jan Roos has calculated the energy density of the vacuum itself, this rho naught, by making an analogy with fluid dynamics. And he calculates that the energy density is about 3 times 10 to the 20th joules per meter cubed, which is comparable to Vallée's own calculation of 2 times 10 to the 20th joules per meter cubed, based on a completely different consideration. So there is somewhat of a corroboration by a fluid dynamic approach to what Vallée has been attempting to do. That, by the way, corresponds to a hydrostatic equivalent magnetic field pressure of 3 million Gauss. Give you an idea. Vallée goes on to show that gravitational forces are due to differences in density of the vacuum energy and consequently of permittivity and permeability. Now, you general relativists will like that because if we can only change the metric of space by changing the permittivity or permeability, we can do all sorts of wonderful things. And Vallée suggests that we can do that through a simpler approach, equation 40, for instance, probably up there over the right side. Gamma, which is the acceleration, the gravitational acceleration in meters per second cubed, meters per second, pardon me, is equal to the inverse of the energy density at the point of measurement times the time rate of change of E cross H, like the Poynting vector, time rate of change. And however, since that rho, the energy density of space, is so great, you have to have enormous fields, E and H, or enormously fast varying fields, quickly varying fields, to produce in a region of space an acceleration that comes even close to that which we feel on the Earth, 9.81 meters per second squared. And now, to wrap that up, using these equations, we can take a look at 3 instances of how we can use Vallée's equations to see what kind of field strengths and frequencies and things like that we might require before we see gravitational and other odd energetic effects. And the first one is up there as A. It is instructive to investigate the charge density required to begin to see anomalous gravitational effects in the so-called cold dense charged plasma pinched by radial Casimir forces, as postulated, for instance, by Puthoff. And using Vallée's equations and spherical charge distribution, I haven't got it up here, but can create an equation which shows that at a distance of 1 micron away, that's 10 to the minus 6 meters, that's 1,000th of a millimeter, from a pinch charge that is 10 to the minus 6 coulombs, or about 10 to the 12th electrons in a little ball of less than a micron in radius, one would actually see, if one were able to measure the gravitational acceleration right next to that pinched huge charge density, an acceleration of what we experience on Earth. It gives you an idea. You have to get 10 to the 12th electrons into a space that is less than a micron in radius, if it's spherical. Another way of looking at these equations of Vallée is down to B. If we look at plane waves now, linearly polarized plane waves in free space propagating in the X direction according to standard kinds of equations, and applying Vallée's theories, we can see that in order to get an equivalent gravitational effect, and Vallée says that accompanying every electromagnetic wave is a gravitational wave, you might say, due to the E cross H. To get the equivalent gravitational effect, one would have to have a field strength of at least 700 billion volts per meter, which, by the way, turns out to be independent of frequency. Nu there is frequency. So you can see that is a pretty high electric field strength. By the way, it's several orders of magnitude larger than fields found presently in plasma work. However, it's only several orders of magnitude, not thousands of orders of magnitude. And finally, drop down to C, and we take a look at the characteristics of dipole oscillation, which may give rise to measurable gravitational effects. And following the development found in a textbook on such things by Lorraine and Corson in spherical coordinates, we can generate an equation and show that the zero-point energy, assuming a zero-point energy of 2 times 10 to the 20th joules per meter cubed, which is Vallée's cutoff energy, a charge such as would be found in this Casimir pinch, this put-off kind of thing, where you've got 10 to the 12th electrons in a tiny space, and a separation distance between the dipoles of 10 to the minus 4 meters, which is 0.1 millimeters, tenth of a millimeter. In one case, if you could oscillate these dipoles at 620 gigahertz and measure them at 1.5 times 10 to the minus 4th meters, just a little bit larger than the separation distance, you would experience a gravitational effect of 7.3 meters per second squared. By the way, that's just shy of 9.81, which is what we are experiencing here. In another case, give you another example, if the dipole oscillated 186 gigahertz and we were looking at it from a distance of 5 times 10 to the minus 4th meters, by the way, that R vector should be to the center point, not to one point, we would only get a 0.005 meters per second squared. You can see that the gravitational effects fall off extremely rapidly as you get farther and farther away from some of these oscillating systems. But that, once again, is using Vallée's theory. In any event, I'll wrap up now and say that it is apparent that within these formulations, there's a critical range of parameters from which it may be expected that we shall see gravitational and energetic effects in the laboratory. Fortunately, some of them have already been achieved, and it is expected that such phenomena will soon be witnessed. It is also hoped that others skilled in physical theory and engineering practice will be able to check out into and expand on the work presented here and produce a set of engineering principles from which commercial applications will result. Thank you for allowing me to go on beyond my time.